we're going to talk even more about dummies because they're important. But they are also complicated, gotta admit. So, particularly, we have lots of interactions, lots of different dummy variables, got a lot of moving parts. So you got to do some work to try to explain all the things that are going on. To explain to your audience, but honestly, also first explain to yourself. When we started with OLS just a couple lectures ago, it seemed straightforward enough. We had a single continuous variable and interpreted the coefficient on that as a slope. X variable goes up by 1, the Y variable goes up by coefficient beta. That predictive amount is relatively simple. But if you add tons of complications and interactions and blah, 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 then it really gets difficult, even for the person doing the regression to understand. Certainly difficult to explain to somebody else that hasn't done all that background work. You got to think about not just how to get the output from the computer, but also what are the best ways to present all this. And the commonly involves joint hypothesis tests, for example, interaction term. It's sensible to test whether some set of coefficients are all zero. Giving interpretations is often helpful to display some predictions. Somebody's predicted wage, particular sort of person, particular example, predicted to make blah, blah, blah. Somebody else predicted to make something else. You got to get a sense of, whether these are plausible even. For example, here's a relatively fearsome-looking econometric model. It says wage is determined by age, sex, education, and then interactions of gender with education. If one of your goals is to impress somebody, then okay, show off that big, ugly, complicated equation there. But if you want to help people understand, then maybe show predictions. So, for example, a 30-year-old female with an associate's degree would get a certain wage. As you plug in term by term, you start to figure out it may look really complicated, but actually a lot of those dummy variables are just zero, and so drop out of the equation. In the bottom part there, I've grayed all the terms that just drop in order to concentrate on a few. That makes it a little more straightforward to just understand, what the heck is going on there? So to remind, and it's worth saying again and again, don't be a dummy about dummies. A single dummy variable is implicitly a comparison between a group with the dummy variable equal to 0 and a group with a dummy variable equal to 1. That implies those groups are each homogeneous to a certain extent. Now, obviously, that's precisely false. There's an old saying, all models are wrong, some are useful. This assumption of the two groups being homogeneous is, of course, wrong, but it may be useful. It shouldn't be too crazy wrong. For example, you might use a dummy if a person has a high school diploma, which would lump together people that got a regular high school diploma along with people who got the GED. In the US, that means they did not graduate at the usual time, they dropped out, came back, completed later. Now, those two groups, people with a regular high school diploma and people with a GED, they might have distinctions in various outcomes. But in some analyses, it could be sensible enough to bunch them together. Wrong, but useful. Now, whether it's reasonable to assume homogeneity may depend on the particular question being asked. It's even more relevant in understanding a common mistake that students make, putting in one dummy variable but omitting the rest of the set. For example, from a whole set of dummies for education, no high school diploma, some college, bachelor's, advanced degree, if I pick out just one, say the dummy for if the person has a high school diploma, and only put that in the regression, then I'm implicitly comparing them with the other group, the people with dummy variable, that single dummy variable equal to 0. That other group are a weird combination of those with less schooling than a high school diploma, along with those with more education, which is probably not at all plausibly homogeneous. So you need the whole set of education dummies. Another case where you and the modeler have a choice is sometimes whether to use a dummy variable or a continuous variable. Now, obviously, sometimes you don't have a choice. Maybe you only have a dummy variable. And for instance, household pulse data doesn't tell us the household income, but rather dummy variable, whether it's in a particular range. But sometimes we have a choice. For example, age. Sometimes age is given. Sometimes it's broken into groups like in the 20s, in the 30s, even broader groups like boomer, or Gen X, or millennial. You can make a plausible argument that Actually, everybody gives their age in a bin. Nobody reports they're, I don't know, 34.68 years old. In many surveys, people report their age in numbers ending in 5 or 0. People lie about their age. Other news. But part of the reason we use polynomial terms for age was we believe that in a model of wage, delta age is not going to be constant. That could be alternately specified with age dummies. Now each age has its own group mean, and the change from 34 to 35 could be completely different from the change to 33 to 34. You might remember learning calculus, worrying about the distinction between left-hand side and right-hand side limits. Back there again, step functions. Now you can argue about which specification is going to be better. There are other examples where a modeler might have a choice. And for example, health outcomes, we might have the person's blood pressure, but also a dummy variable for if they have high blood pressure. Or if we're doing sports analytics, we could use the win-loss, or could use points scored versus points against. That former, the win-loss, is going to be binned into dummy variables, while the latter is going to be a little closer to continuous measure. Usually it's better not to throw away information. But there are other cases where there are discontinuities genuinely, in which case those can be really useful in the modeling. Somebody who does 3.9 years of undergraduate education did not get an undergraduate degree. They got close, they didn't quite finish. That's probably different than somebody who actually gets a degree. So the people or the person doing the modeling has to know a bit about what these cases are and where it's plausible to think they're going to be discontinuities. Now, usually when we have panel data, we have a lot more dummy variables. Hooray! Yeah, but you got to do even more work to get it right. Panel data is repeated observations over time of multiple units. For example, some CPS surveys talk to the same person each month, but lots of different people. That's a panel. Pretty short for a term. Cross-section would have a number of different people or units at one particular time. A time series would have data on one unit over multiple times. Panel is kind of a rectangle of data, both lots of observation units and lots of times for each unit. For stock market data, the price per day of one stock would be a time series. If I have a whole lot of stocks, maybe the S&P 500, then I have a panel. Company might look at sales in different store locations over time. A repeated cross-section is different. For example, the CPS does follow people for 1 year, but not longer. 2018 CPS is a different group of people than the 2021 CPS. From that, you could say the average wage for a college graduate has changed, but you're not looking at the same people. A pooled sample is going to be the same idea. Typically for panel data, we'd have two sets of dummy variables, a unit effect and a time effect, which, apologies, that's notation hell. But in the service of trying to add clarity, we sometimes got to go through it. The T subscript here indexes time. The J subscript indexes the unit. Each observation of X and Y are for a particular date and a particular unit. So we have Y, T, comma, J, the output of a particular unit, J at a time T. And then there are K different X variables. Put K as a superscript, not a squared term, but just a different index. There are multiple X variables. We have Y, T, comma, J equals alpha J, those are the unit fixed effects, plus gamma T, those are the time fixed effects, plus beta 1 X1, different at each time T in unit J, plus beta 2 X2, T, comma, J, and so on for all of those K different X variables. Then there's an error term. Note the distinction between alpha J and gamma T. The alpha J are the unit fixed effects, which do not change over time, so there's no T index. Whereas the gamma T are the time effects, but they're common for every unit, so there's no unit. So let's look at an example. Suppose I'm analyzing data for a business that has multiple stores in different locations. Each column is annual sales for 8 different locations of the same store. These are year effects. There are strong years where everybody sells a lot. And then there are weak years where everybody doesn't sell as much. Those would be the time fixed effects. Then I take account of the locations. There's some locations that are just really good. They're really busy. Every year they do a lot of business. Other locations are a little quieter. They don't get as much. So if you wanted to evaluate how different stores are managed, say, we understand that while there are some stores where business is always good because of location, it's not necessarily the good manager. It's just a good location. Similarly, some years are good or bad for every store, and you can't attribute that to the manager. To do the analysis, you got to create dummy variables for the years, dummy variables for the units, regress y on whatever other x variables, and add these sets of dummy variables for the years and the units. Now, those dummy variables mean we cannot include any x variables that do not vary across the unit, and similarly cannot include any x variables that do not vary over time, because there's that time fixed effects. Those fixed effects are going to soak up a lot of variation. The bottom line is dummy variables are, they're a real pain to deal with and pain to interpret, but on the other hand, they can be very useful. So you got to learn how to interpret them and use them, because they'll get you a long, long way on a lot of your predictions.